So yeah, uh, I think we should wait for some time before starting the discussion. Let's say 6:05, then we'll start. Uh, Good evening, Narendra. Can you hear my voice?
Oh, nice, sir. Good evening, sir.
Yeah, so you can see the screen and hear voice properly, right?
Yeah, sir.
Okay, okay. We'll wait for a couple of minutes. If anybody joins, fine. Otherwise, we'll start. So I think it's 6:05. So we'll start. If anyone joins, uh, let them come. But otherwise, we'll get late. So yeah, today we are discussing about this week 6 assignment or syllabus of week 6 for the course of concepts of thermodynamics. And as usual, we'll start first with some concepts that were covered in the last week by professor. Actually, to be honest, for this assignment, there is only one major, you can say concept wise, only one thing is there. So essentially, what we are trying to uh, study here or for this scope of this discussion is regarding uh, uniform uniform state, uniform flow. uh, you can call it as equation or so. This is what in short form you can write USUF equation. So essentially, as the name suggests, there are two assumptions. Basically, this is nothing but the Reynolds transport equation, or a mathematical formulation by which you transform control mass system into control volume system. Uh, a steady version or steady state, steady flow version. It was discussed in the last discussion or last class. In this class, the another variation of that same basic principle is here. So the additional assumptions are what the name suggests here. First is one second. I'll write assumptions, because if you understand why such system or why such equation is there and what all the assumptions behind it, you'll know where to apply it and where not to, and in which case control mass system, like considering your system as a control mass or control volume, in that also uniform control volume or steady control volume, like in classroom you can solve it easily because these are compartmentalized in each week, so there is no confusion. But imagine if you are doing, you are applying thermodynamics to some real application, real system. There you want, there will be no one to tell you which sort of uh, which sort of which what is the type of the system, whether it's a control mass, control volume, or something else. It I mean, like, if you are on your own to decide it, uh, then it's better to have a good background, good understanding of these different type of equations that we are studying here, and what all the assumptions that are behind them. And then maybe you can model your real system by taking some approximations which will closely resemble with these assumptions that we are going to discuss here. And you know then maybe you can predict your system's behavior using thermodynamics. So but since we are looking, uh, like, for this course we are taking it week by week, so many of you may find it trivial, that why we are doing this. We solved steady state, steady flow last class. Then why just you are changing the name and doing some manipulation in the governing equation, and you are taking some classes. So that is not the purpose. You should understand real systems. Some of the real systems will follow this type of behavior, or some of the analysis that you want to do for real systems may follow steady state behavior. Some may follow this uniform state behavior, and some may follow this control mass. So it all depends on your application. So considering that in mind, please understand that this is not a trivial topic. And I mean, from conceptual point of view, there is not much. But if you appear for any interview or any uh, like research interview or BARC or ISRO, and if you say thermodynamics is your favorite subject, or if you give it as a subject on which questions to be asked, then you should know these things in detail, and that is what uh, the whole thing is about today. So essentially, the first assumption is, as it is given in the name only, uniform state within the control volume. So CV is for control volume, short form. By this uniform state, I mean, let's say there is some extensive property of the control volume, and it is represented by n, which is a common notification or common symbol that we are using in this course for extensive property in RTT part. So if your control volume undergoes a process from 1 to 2, uh, what we are interested in, or what is under the scope of thermodynamics, is what is the state of your control volume at state 1, and what is condition of your control volume at state 2. And this uniform state assumption is essentially, one second, there was some within the control volume. So this uniform state assumption essentially tells you that when you are at this state 1, there is no spatial variation in your control volume with respect to this property, extensive property n. These can be any properties, extensive properties like volume, mass. It can be anything, and you can say the same for like intensive properties as well. But extensive properties is a more generic term. So if your control volume is like this, uh, and there is by uniform, I mean, some of you may know, but if you don't, when you say steady, that is related to time, and when you say uniform, that is related to your uh, domain or space that you are working with. It can be 1D, 2D, 3D. This is a 2D, I mean the square that I have drawn here as a control volume. It is a 2D type of spatial distribution. So there you are assuming it to be uniform. And someone might ask, how can you do like in real systems? There will be some variation within the control volume, right? For example, if I take this control volume and apply it to a turbine problem or compressor problem or nozzle problem, so there within the nozzle or within the turbine, there will be spatial variations, right? But the assumption essentially tells you that you have given your system enough relaxation time so that whatever internal gradients were there in your system, they are relaxed and your system has returned to a uniform state. In real applications, uh, this cannot be possible at every state. So that's why we are dealing with initial and final state, which is represented by 1 to 2. We can't say anything about what was the state of your control volume within 1 and 2. How it reached there and all, that information cannot be conveyed when you do this, when you assume uniform state between the state points 1 and 2. Between 1 and 2, there can be, you know, there can be, I think this is more correct. So you should clearly mention uniform states. And, but like in general, what we do to get away with this complication, we just say that, we assume quasi-equilibrium process. So that essentially means at each state your system will be in equilibrium, and your system can be in equilibrium only if there are no internal changes in the extensive properties or any property. So that's how it is. I mean, it's quite conceptual, and you should develop this intuition here. Uh, like I cannot write this part also between states 1 and 2. I mean, that is still valid, but the unspecified assumption behind that part will be that I am assuming the system is going from state 1 to 2 in quasi-equilibrium manner. And then you can just say that between 1 and like at 1 and 2, the system is uniform. That is also okay. Okay, then yeah, so there will be no spatial variation across this. So I hope I have elaborated enough. If anyone has doubt, you can ask me, or I mean, not now, maybe later. We'll be meeting again and again. So then the second assumption is uniform flow. So I think this assumption was already discussed in the last class, where we discussed steady flow, steady energy, steady state, steady flow energy equation. Uniform flow, essentially it is valid at the control volume surfaces, like uh, where you do the surface integral, or where inlet outlets are there. In control mass system, these are boundaries. Here also we can specify boundary, but at least you should know the terminology. Here we call it as surfaces. Uh, so at control volume surfaces, which can include inlets, outlets, there you assume uniform distribution of flow. So essentially, if you have a control volume like this and your inlet is over this smaller cross section area, if you zoom it up, I think I told you this last time also, if this is your inlet, uh, so if you zoom it up, maybe it will look like this. So your flow will be taking through this, this much thicker.
Hello, sir.
Hello. Hello. Hello, Roshan. Roshan was asking something. What happened? 1 second. Roshan Kumar. I am not able to hear you, Roshan. You are muted, I think. Can. Oh, he's disconnected. Narendra, my voice is clear?
Yes, your voice is clear, sir.
Okay, so maybe he'll reconnect, then we'll see what he was asking.
At
But
present,
anyway,
he left the meeting.
I think there will be some network interruption,
Yeah,
maybe.
yeah, yeah, sir.
Anyway, we'll go. If he joins again, we'll talk. So essentially, yeah, if you zoom in and if you say this is your height of inlet, uh, so you know that at boundaries there will be no flow because of no slip condition, and there will be, if you draw the velocity profile, it will look like parabolic, assuming your flow is laminar. Then over each point on this boundary, maybe I'll use some other color for just showing you this. I mean, you might already know this, but still, anyway, we don't have much to discuss conceptually this time. So if you consider this red line, at each point on this red line, the flow is, velocity is varying. So rho AV, if you can take a small elemental area of dA, at each dA, your mass flow rate is varying. So this uniform flow assumption essentially allows you to take a surface area averaged properties at the inlets and outlets. So that's it for this assumption. So if you have these two assumptions, you can, professor has told you how to derive this US UF equation. I'll just write the final form here, because if you do that derivation, then we'll not have any time to do anything. So this is your net energy supplied to the control volume, and this is valid for control volume undergoing.
Hello, sir.
Hello, sir. Yeah, tell me. Yeah, Roshan.
Hello.
Tell me. I am hearing you. Can you hear me?
सर आप कौन सा क्वेश्चन मतलब कि डिस्कशन कर रहे हैं?
क्या हुआ? ये दिस इज थर्मोडायनेमिक्स
डिस्कस कर रहे हैं?
अरे नहीं, क्वेश्चन अभी चालू नहीं हुआ है, 2 मिनट में हो जाएगा. प्लीज 2 मिनट्स, कैन यू वेट?
ओके सर, अभी मतलब कि आप ठीक है सर, थोड़ा देर में स्टार्ट कीजिएगा.
हाँ ठीक है. ये टिंकू कुमार, हाँ ठीक है. ओके फाइन. So the form will be like this is your heat for the control volume, heat interaction. Then this is a, I mean, you might know this already. This is the typical form. This will be equal to work done plus Let's write it out. This part, though, this is clear, and last time it was approximately like this only. But now, since this is a here there will be one d by dt of control volume term, which you, when you divide, it will essentially look like this: m2 u2 plus v2 square by 2 plus gz2 minus m1 u1 plus v1 square by 2 plus gz1. So this is the whole thing. These last two terms are nothing but your d by dt of your control volume. You expand it this way, and this is for energy. And if you want to do the mass conservation equation for the control volume, you can write it as like this. In second, I should not write m dot here. This is wrong. So anyway, it will be mi minus me. So the subscripts are I for inlet, E for exit. One is your initial state, 2 is your final state of control volume. One important point to note here is when you write mi and me, then in the bracket you write enthalpies, whereas when you write m1 m2, you write internal energies. And the reason behind it should be clear by now that it is because when you are considering inlet and outlet, there is a work done required, additional work done required for maintaining the flow, which is called as flow work or flow energy. Then if you consider that, your internal energy will be added by PV term and it will become enthalpy. Whereas when you consider only control volume, there is no flow work inside the control volume. So that's why only U term will be there. So now we'll go to the problems. Question 1, I have some sample questions here. Given there is a tank. I will draw it this side, and this is a tank. The volume, one second. Volume of the tank. I will write. I will use this symbol for volume because we are using for velocity. Anyway, we are not taking velocity many a times, but still let's use different symbols. So this is 2.5 liters. So I think you should know the conversion factor of liter to meter cube. It will be 2.5 into 10 to the power minus 3 meter cube. And it's a tank filling process. So there is inlet I.
बोलो हेलो हेलो
हाँ बोल ही रहा
सर
हूँ.
माय रूममेट टेलिंग मी सर सनी
Can you mute yourself, Sinku? So this. So this tank filling process is going on, and this is ammonia pipeline through which the ammonia is coming and getting filled in the tank. And also initially the tank was empty. So this will be m1 equal to 0. And finally, like in the question it is mentioned that when the when the tank is filled, the total mass of ammonia entered in tank is 10 grams, so which is essentially 0.01 kg, and this will be our M2 because this is your final mass of the control volume. And before we move on, this is our control volume, the tank itself. We take it as a control volume. So I'll write it here. So then what else is given? The temperature of tank, it is maintained at 30 degrees Celsius throughout. So your temperature of control volume is essentially same at state 1 and state 2, and it is 30 degrees Celsius. And the ammonia that is coming from the line is at 25 degrees Celsius, and it is a saturated vapor. So this much information is given. Now to find, it is a two-part question. First, you need to find what is the final pressure in the tank, and second, you need to find what is the heat transfer throughout this process. So yeah, since this is ammonia, you may not have the property table for this, but if you refer any standard book, in the last appendix section you should have ammonia table. If not, I'll give you some properties which are required here. But before we move on, we should write the uniform state, uniform flow equation, and we can eliminate some terms. This is actually this may be looking like a trivial exercise, because every time we write this and then cut most of the terms, then why not directly cut everything initially only, right? So you may feel that, but you should, if you have enough practice, and if you are confident that you'll not make any mistake while solving such problems, then go ahead. You can in the start only you can eliminate many terms, but since this is our first problem, I'll just keep all the terms and then we'll go about it. And there will be work done term. Yeah. So now M1 was 0. It was given in the question. So I'll use, so M1 was 0. So this whole term goes to 0. There are no exits. So this ME term also goes to 0. There is no work done on the control volume or by the control volume. So this term also goes to 0. And amongst the terms that are remaining, we generally 99% of the time we neglect it should be like this. We neglect this kinetic energy and potential energy variation. So these terms are gone. Here also you can this whole term was 0 only, so no point there. So essentially it boils down to the Q plus Mi Hi equal to M2 U2. So the whole bigger equation it just boiled down to these three terms. And first part, it is asking for pressure. So what do you know? You know the tank of volume of the tank, which is 2.5 liters, and you know the exactly what is the mass at the end of the filling process, which is 10 grams. So you can calculate the specific volume at the end, which will be volume divided by M2. So if you do the calculation, you should get 0.25 meter cube per kg. And now this is the time when you need to look at the steam tables. Sorry, not steam table, property tables for ammonia. And it is mentioned that it is a 1 second. It is a saturated vapor or saturated gas, saturated vapor form. Saturated state, I think I should write. Vapor, you may get confused with the water vapor thing. So it is saturated state in the gaseous form. So that this is essentially Vg at 30 degrees Celsius for ammonia. So now, I mean, if you don't have the steam table, what you need to do is you need to go to the steam table, and you should go to the superheated steam table, because there you will easily find the saturated properties in the gaseous state. And then like to find pressure, you need to do some interpolation. I'll tell you the table. I mean, you can do it on your own, but it should look like this. This is meter cube per kg, and if you check it, these values are there. So this is your essentially this thing. So 0.28103 and 0.23152. So your specific volume is 0.25, which lies between these two values in the property table. So you need to do the linear interpolation, and if you do this calculation, you should get P2 equal to 562.7 kilopascal. I am not doing this calculation. I leave it as an exercise for you, but this is a fairly straightforward calculation. You should be able to do it. Now the second part is interesting. For second part, what do you need? You know, I mean, like here, this let me denote it as equation 1. You can write mass balance also from mass balance for control volume. You know, M2 minus M1 is equal to I think I minus E. Mi minus Me. So now here there is no Me, so it will go to 0. There was tank was empty at the starting point, therefore M2 is equal to Mi. Put equation 2 in 1, you get Q equal to M2 U2 minus Hi. So now you know M2 because it was given in the question. Again, you need to go to the property table of ammonia and you need to find U2. U2 you'll find in the same fashion as you found out pressure. So there will be another column here of Ug, which will be in kilojoule per kg. So you need to look up there and do the linear interpolation and you'll get the value of U2. Now for Hi, it was mentioned that the tank, I mean the ammonia gas coming to the tank was at 25 degrees Celsius and it is also a saturated vapor or saturated gas. So then you need to go to the property table and look up for temperature of 25 degrees Celsius what is Hg value, and if you plug these values here, I'll just give you the value. You can cross check if you want, or you can just leave it at that. It's your call. So U2 should come around 1370 kilojoule per kg, and Hi will be 1463.5. So finally you are getting minus 0.935 kilojoule. Now this is your answer. So you have solved the question, but what is the interpretation? I mean, this is a numerical calculation that you did, but what it tells is Q is negative. And as per our sign convention, when Q is negative, Q is lost by control volume to surrounding. So, you know, this means that during this tank filling process, there was net heat loss from the control volume to the surroundings. So that one assumption, one important conclusion is there. Essentially, if you want to avoid this, you can, insulate it or something, but then your T2 will change because now the heat is not getting lost. So yeah, so this is how you solve this type of question, and this template will be followed everywhere. I mean, today I'll be taking more questions, but generally, it is similar type of problems. Then let's go for second question. Again, this is also similar question only. So there is a tank given. There is a tank. I'll draw here, and there is again supply line from which there is one connection, and given is that air is there, air filling process, but they have mentioned that this is adiabatic. I mean, there is no heat loss. In the last problem, there was heat loss from the tank since it was not insulated. This is your supply line. So there is one valve, but anyway, that is not that important. You can just take I here. You'll be safe. So again, volume of the tank is given as 25 liters, which is again 25 into 10 to the power minus 3 meter cube. Initially it was evacuated, so M1 was 0, and the supply line, air coming from the supply line is coming at 20 degrees Celsius and supply pressure of 800 kilopascal. Then finally, when the tank filling process is complete, the final pressure of the system at the state 2 is 600 kilopascal. These are the given data, and it is adiabatic. So this is also given that Q is equal to 0. So now you have to find what you have to find. First, you have to find final temperature in the tank, and second, you have to find what is the mass of air which entered the tank. So these two things are to be found. So again, we'll start with the first step should be defining your control volume. So the whole tank is my control volume. Now when you write this UF equations, I am writing both together, mass and energy. So if you write mass, you have M2 minus M1 equal to Mi minus Me. So straightforward, M1 was 0, so this term goes, there is no exit, this term goes. So this gives you M2 equal to Mi. Essentially that means whatever mass entered through I inlet, that is the final mass of your control volume or the tank. So that makes sense. Now you can write the energy equation. What I'll do, since I'll just mention here, neglecting kinetic energy and potential energy changes, because we wrote the whole equation first and we realized the kinetic energy and potential energy changes are anyway neglected. So from here onwards, I'll not write them again and again. I'll just write the important terms so that it looks slightly less congested. So if you do that, you have Mi, Hi here. It will become M2 U2 minus m1 u1 plus me he plus w. You can remember this form of equation also, but you should mention this assumption there. If this assumption is not there, then this is not correct. Again, here m1 is 0, me is 0, and there is no work done on the control volume or by the control volume. So essentially it again boils down, and this mi is equal to m2 from here, from equation 1. So again, you have q equal to m2 u2 in bracket minus hi. This is a typical equation. And since we are talking about air here, I'll slightly deviate. When you consider air as an ideal gas, there is an interesting one second. And this is equal to 0 because it's an insulated tank. So one note, I think this thing was mentioned by Professor Sumant also, and this question is asked in many competitive exams. If you see previous GATE or ESE papers, old papers, you will find this question typically. Uh, you know, for tank filling with air, and this is evacuated tank initially. The relation between supply air temperature and final air temperature in tank. So essentially, the terminology of the question may be changing, but essentially what they are asking is what is the relation between Ti and T2. So, and the inherent assumption is the tank filling process is fast. So you can assume there is an adiabatic. This is an adiabatic process. So Q equal to 0. So this will be similar to what we have done and what we got in this equation 2. So in the end, you'll do U2 equal to Hi, and then you assume air as an ideal gas. So your U will become CvT2, and your Hi will become CpTi. And if T2 equal to Ti, which is true for most of the cases, which is like the temperature at which the air is supplied to the tank, that will be the final temperature of your system or control volume. In that case, uh, sorry. Yeah, sorry. If I assume this, then the problem is not like trivial only. So essentially, we are interested in the relation between T2 and T1. So Cp by Cv, this is Ti. So essentially, T2 will be equal to gamma Ti, and we know for gamma of air is 1.4. So T2 will be greater than Ti. So this type of one-liner is asked in many competitive exams. You might have seen them, but if you not, you will come across them, or this is the typical question from this part of the syllabus that is asked. In interviews also they'll ask this: why the temperature of the system at the end is higher than the inlet or the supply temperature of the air. So essentially, what happens? Your air is coming at certain temperature, but it has to do some flow work, right? So when it is filling it, it is doing some additional work in the form of flow energy or flow work, and that's why your final energy of the system is higher than your supplied energy, and therefore your temperature is also higher. So I mean, I have deviated from the problem, but this type of questions are asked multiple times. So let us come back to our problem. So from equation 2, I can write U2 equal to HI. Now the thing is, uh, how will you find HI or U2? Your objective is to find T2, because in this question you need to find T2 and M2. This will be M2. So T2 you need to, U2 will somehow give you T2. Now what it is mentioned in the question that the air is supplied at 20 degrees Celsius and 800 kilopascal. You need to go back to the property table for air. Here you can't use CPT. I think there will be a difference in the property because temperature is lower, pressure is 8 bar. So there may be some slight variation, but if you don't have table, you can't do anything, then you have to go CPT. But here, if you can go to the property table of air or ideal gas, we are assuming it as ideal gas here. So if you go there, you will get HI. So HI from property table, and you should get the HI value of, if you go to the table, you should get the value equal to 293.65 kilojoule per kg. Let me check once. If I do CPT, 1.005 into 20 degrees Celsius is 293 Kelvin. If I do, if I calculate HI as CPTI, I am getting 294.46 kilojoule per kg. So you can see the properties or the values are not that far. So I think Narendra asked in the last class, if you do anyway, it will be similar only. But if you have table, go with the table. That will be the exact answer. And CPT will have some sort of approximation of CP in that. So if you do that, now you know the U2 value, and you can again go back to the table and back calculate T2. You should get T2 as 410 Kelvin. I mean, you can do it in degrees Celsius because your initial values were in this thing. So it should be 137 degrees Celsius. This will be your final temperature. So you can see your inlet temperature to the system or the tank was at 20 degrees Celsius, but finally you landed way above this thing, T2. I mean, T2, if you see, it's 137 degrees Celsius. So that's how that happens when you don't allow heat to be dissipated from the tank. The temperature will rise like anything, and you need to be considering this while designing your tank. So now the second part of the question is M2. This was asked. So to find M2, since you are assuming it as ideal gas, air as an ideal gas, you can write M2 as P2V by R T2. T2 you found out, V is volume which is given, and P2, it was also mentioned in the question that this is 600 kilopascal. So if you put everything, and R is for air, it's not the universal gas constant, it's a characteristic gas constant for air. You should get this value. This is the correct answer. So this is for second question. Actually, these type of problems are, not much to it. So I understand if you are getting bored, but we have to do those exercises, to not to make mistakes in future. So we'll go to the third question or the next question. This is slightly different. Here you have a system or the control volume like this. This has two-phase mixture. This is liquid. Here it's vapor. And there is one exit at the top. I think this is a boiler. Yeah, I think. I mean, this is typically a boiler system. There will be some wall or something, but you'll have exit here, and heat is provided to this control volume. So essentially, it's a boiler. So this is our control volume here. Now what is given? Volume of the tank is 200 liters, which is 0.2 meter cube, if I'm not wrong. Yeah, I think it's 0.2. And initially water is at 100 kilopascal, so P1 is 100 kPa. X1 is given, which is new, which is a dryness fraction or quality. It is 1%. Then heat is provided to the system or the control volume. So pressure and temperature increases, and when pressure reaches 200 kilopascal, we open this valve, and saturated vapor at 2 megapascal. Oh, sorry, it's not kPa, it's MPa. So it's 200. Oh, it's actually 2000 kPa, so it will be 2 megapascal. So 20 times the pressure is increased 20 times, and the saturated vapor is flowing out. So this is, you can assume, as PE, exit pressure, and quality at the exit is 90%. So this is given. I'm sorry, I made a mistake here. Please correct if you have mentioned written anything else. So it is written that the safety valve, this is the safety valve shown here in the figure. It opens when the pressure reaches 2 megapascal, and saturated vapor flows out at 2 megapascal. So this is your exit pressure, and it's a saturated vapor. And what happens then, as the vapor is leaving, your dryness fraction in the system will decrease. So the valve shuts off when your final pressure becomes 2 megapascal, and your dryness fraction again falls down to the 90%. So then the exit, it stops. So this is our final state. And to find, you need to find two things here. One is what is the mass of the system that is exited. So ME. And one more thing, I think it will be heat or something. What is the total heat supplied to the control volume? So these two things are there that you need to find. So essentially, this is a boiler. If you if you want to get a physical sense of it, what is happening? It's a boiler. When the pressure reaches certain value, we take saturated vapor and let the pressure also should fall, but here let's say pressure is constant, the dryness fraction falls. So this is the boiler. So now again you can write your control volume is the whole tank or boiler. You can write again, the solution will go like this. If you write for mass continuity, M2 minus M1 will be equal to Mi minus Me. Now here there is no Mi. There was some initial mass in the system, there's final mass in the system, and some mass exited. So essentially Me can be M1 minus M2. So basically the difference of mass that exited the system. And again, if you write energy equation, the UF equation, and neglecting kinetic and potential energy changes, then you should get Q. You can write 1 to 2 as M2U2 minus M1U1 plus MEHE. Here there is no work done, so the W term goes, and there is no Mi, so that whole term also goes. So only these three terms are remaining. And Me is M1 minus M2, so you can replace that also here, so that everything becomes function of M1 and M2. So that is in your hand. So basically what all we have, let's go to the question. The total volume is given initially, E1 X1 is given. So you can start by going to the saturated steam or water vapor, like saturated water table you can call, because initially it was all water, right? X equal to 1% means it's almost almost liquid everywhere. I mean 99% by volume is liquid, or by mass, sorry. So if you do that, you need to find V1, that will be Vf1 plus X1 Fg1. Now you have X1, but what about Vf1 and Vg1? So you need to understand that initial pressure was 100 kilopascal, which is 1 bar. So that way you can get the value of V1, specific volume. It should come around 0.0179 meter cube per kg. You know the total total volume was 200 liters, so 0.2 meter cube. So you should get M1 as total by initial specific volume. So if you do this calculation, you'll get M1 as 11.13 kg. So M1 we got. Now U1 also you can calculate same way. U1 will be UF1 plus X1 UFG1. It should be close to the UF value, because X is 0.01. That is also one sanity check you can do if you want to cross check your calculations. So these two values you get. So you have M1 U1. Now what about HE? So HE also you need to find out, right? So you know that when the steam or when the water saturated steam is leaving, the exit pressure is 2 megapascal, and it is a saturated vapor. So you go to the steam table, water steam table, and you get HE as Hg at this thing 2 megapascal. And if you get this value, you should get 2799.51 kilojoule per kg. So now we have HE also. Now the question is how to get ME or M2. So What can we do? So we know the final state, right? In final, it was given that finally, when the system stops or the exiting process stops, the system pressure, control volume pressure is 2 megapascal and quality is 90%. So again, go to the steam table and you should go to the saturated water table. I mean, uh, since the quality is 90%, you can't go to the, superheated ones. So you go to the 2 megapascal pressure value and get your V2 again as same formula. X2 90%, so 0.9, and VMG2. So these values and if you do the calculation, you should get the value as 0.8978. So this is your specific volume. You can get U2 in the same fashion. U2 will be G2. So if you do this calculation, I expect you to do these things if you are, because here also if you are not careful, you'll make some calculation mistake and everything will be wrong. So even though I'm giving you the values, you should at least do some work on your own. Then you can get M2 as total volume of the system divided by the specific volume at second state. This is 0.2 by 0.8978, and if you do this calculation, you should get 2.23 kg. So now you have M1, which is 11.13 kg, M2 as this. So therefore ME, which is difference of these two, M1 minus M2, we got that initially here from equation 1. So if you do this calculation, if you take the difference, you should get 8.90 kg. So essentially this much mass of water left the boiler by the time this process stopped. And again, since you know all the mass values, you can plug it in this Q2 equation, Q1 to 2 equation, which is given by second equation 2, and you should get the final value. And here also you should understand that if your calculations are correct, Q should come positive because it's a boiler. You are supplying heat to the boiler. You are not taking heat out of the boiler. So if by some magic your value is coming negative, please go back and cross check everything. It should not come negative. It should come positive. So in this case, it should be 25.46 megajoule. You should understand one thing. Now, till this point, whatever values of Q we are getting, it were in kilojoule. But here it is in megajoule. So almost 1,000 times. So you should understand when it is a boiler, the values should be in megajoule ballpark figure. So it's 7.5. I'll take one more problem and then we'll stop. Actually, these problems are, not that interesting, I feel personally, and I agree if you do the same. But we have to go through this, so let's get over with it. Finally, yeah, this is an interesting question. This was.
Hello, sir.
Bolo Narendra.
Sir, in this question, that exist state is given. It is a saturated vapor.
Yes.
There is one similar question in the assignment. No doubt, I have already submitted my assignment, but that answer is not any matching. That in that same question is given, but that exist state is not any defined there. My exist state is not defined.
No, which problem number? Number
Problem of the assignment.
number याद है number कौन सा number है?
Number 9 and 10. Last
अच्छा,
question.
अच्छा.
I have first part I have calculated very correctly. Quality of the water. I got the answer. and in the second part, find amount of the heat transfer.
One
And
second.
here written that temperature remain the constant, 250 degrees centigrade.
Okay, 1 second. I am opening the assignment. Internet is too fast. Question number, which one?
Last one, 9 and 10.
The 800-liter rigid tank initially
Yeah, yes.
contains water at 250 degrees Celsius, which is 50% liquid, 50% vapor. A valve at the bottom of the tank is opened. Liquid is slowly withdrawn. Heat transfer takes place such that temperature remains constant. Okay. Actually, I am not supposed to discuss the assignment problems, but anyway, only you are here.
No, already I have submitted.
Uh,
Already I have submitted the assignment. Everything is nearly correct. But my doubt is that, no doubt, Suman Chakravarti sir rightly point out this anything. What should be the, if state is not given, then what should be the enthalpy, exit enthalpy? In case of
Average.
the average, in case of the ideal gases, you have to take the average. And he also taken the one problem, but in that any problem state was given like this problem, the saturated vapor. He has taken again the average. But in this any question, that state is not given.
But here it's a water, right? It's not ideal gas also, na?
Yes.
So there also the difference is there. But do you need this thing? Do you need that assumption? Tell me one thing. If you write
I have assuming
one second.
I have taken the HFNA enthalpy of the water, and I got the answer, but it is not exact nearer to the answer. Just
We'll do
little
one thing. We'll do one
representation.
thing. Narendra will solve this one only. Just you help me with the values.
Yeah,
Uh, so let's say this is the liquid part and this is the vapor, right? So
okay.
and I think it's insulated. It's not mentioned. No, no. Heat transfer takes place, right?
Yeah,
Uh, so
it
that the
transfer.
temperature remains constant.
Hmm.
So volume is 800 liters, which is zero point 0.8 meter cube. T1 is 250 degrees Celsius, and the temperature remains constant. So this is T2, and it is 50% liquid and 50% vapor by volume.
By volume.
Okay, so by
Hmm.
volume mentioned.
So you will get a VF equal to the zero point 0.5 into the total volume. It is a 400 liter, and the VG you will get again 400 liters.
Okay, so zero point
Ah,
0.4 meter cube. It is again equal to VG1.
yes. Yeah.
So a valve at the bottom is opened and it is withdrawn. Heat transfer is such that this happens. What is the quality of water in stage 2? So how
Yes.
did you proceed about this?
So that VF and these are not VF1 or the VG1. That is the total volume of the water and volume of the vapor.
Sorry. This should
Uh,
be capital
uh,
V.
the sum is the total volume.
Uh, okay.
Mm. Then we'll get the, I calculated the mass of the liquid, total VF divided by the specific volume VF. That VF
How
is
did you
VF
get
is
the specific volume at T1?
temperature is given 250.
So you from here you got a small VF1.
VF1. So we'll
Is
get
the
MF.
what is the value? Spell
VF
out
is
the value.
0.001251.
0.00.
0.001251.
It will be in meter cube per kg, right?
Yeah. So we'll get the
So
MF.
MF1 that will be
It is coming 319.74.
319
0.74.
kilogram. Correct.
Of the vapor.
This value is correct, huh?
Yeah, sir.
Okay. What is next?
Mass of the vapor, mg.
Okay.
That is Vg divided by specific volume, small Vg.
Like this, huh?
That is it again at from a temperature 250.
Understood. So, this
So
small
answer,
VG1 value is,
from temperature 250 at a temperature 250.
what is the value?
Answer is 7.9792.
7.97
92.
meter cube per kg, huh?
No, this is the mass, total mass, mg1. That is not the volume. I am
Tell me the volume and mention the unit.
volume is 0.05013 meter cube per kg.
This is VG1, huh?
Yeah, yes.
And what is the final
mg
volume?
7.9792
Mm-hmm.
kg.
Hmm.
Uh, we know the mf and mg1, therefore you will get the m1.
So M1 will be summation of these two,
Summation
right?
of the yes, sir. It
Then
is 327.7192.
hmm.
Also, we can calculate the x1 if suppose required.
No,
mg
quality of water in stage 2. So X2 is
uh,
required, right?
if required to calculate the internal energy U1, we may
Acha.
require the x1.
So X1 basically will be mg1
mg
by
divided by
M1.
m1.
So from here you can get U1.
Yes.
It will be UF1 plus X into UFG1. Correct, no?
Yes, sir.
Then
Then state 2,
hmm.
half the initial mass is withdrawn.
Acha.
Therefore, me mass at exit mass is kept. That is equal to the half of me, m1. Initial mass is the
Total mass,
m1.
huh? Okay, so your ME will be M1 by 2.
m1 by 2.
So you'll get
And
some.
by sir energy balance, me here mi equal to the 0. There is no inlet mass.
Correct. So your
me equal to the m1 minus m2. By knowing that finally we may get me equal to the m2. That is mass remain in the tank.
It will be
me again.
This will be ME minus MI, na? Yeah, MI minus ME. This will be minus, right? Here, minus sign.
Yeah.
So M2 will be M1 minus ME, which will be M1 by 2.
Yes.
Okay. So you know this value, right?
Yeah.
Okay. Now
m2 from the equation, I think m2 will equal to the me after solving.
So M2 and ME are M1 by 2, na?
Yes.
So they are same and they are half of the initial total mass.
So it will be the 163.86 kg.
Okay, 163.86. Fine.
Next. Then we have to calculate the dryness fraction, quality of the steam at 2. For that one, we know the specific volume at 2.
How did you
mass. We know the mass m2 is known. Therefore, v2 equal to the total volume divided by mass m2. Total volume is the volume of the tank 800.
What is the
into
value?
800 into the 10 raised to power 3 divided by M2 163.83. The answer is 0.004883
Okay.
meter cube per kg.
Hmm.
And it is a two-phase mixture. Therefore, V2 can write VF2 plus X2 into the VFG2.
Hmm.
You'll get the quality.
How did you find VF2 and VFG2?
Again, temperature is the same at a 250 degree.
So basically they are at 250 degrees. So these
Yes,
values will
sir.
come from the steam table,
Yes,
and
sir.
the next two will be V2
Point
minus
zero seven
VF2 by
point
VF.
zero seven four three one.
ठीक है. I mean this matches, right? So option B
Yeah,
should be correct. Huh?
correct. Yes, sir.
Did you check the answer? Is this the
Yes,
correct
sir.
answer?
Correct answer. 0.07 option is given.
Okay, fine. Next, amount of
The,
heat transfer.
the
So
finally
if
after
I'm right, it should be like this, na?
uh,
M2U2, M1U1 plus
plus
E.
MEH.
Hmm.
In this any equation, sir, we know the M2. We can calculate the U2. M1 known. U1
Hmm.
we can calculate. ME
So this
also
whole
known.
thing is
My
known.
question is for the HE. ME
Hmm.
also known. My question
Hmm.
is the
What is
enthalpy.
your question?
Here enthalpy HE
Hmm.
because state is not given, only temperature is given 250 degrees. Then is
What
it the HF? Yeah, HG, yeah, it's yeah, average of these things.
uh, average of what? See, the temperature is 250 degrees Celsius, right?
It
At
is
1 and
same.
2.
Yes.
So,
We cannot take average.
I mean, see your HE. Uh, see your water is exiting, right? Liquid water is
Uh,
going out of the control volume, na?
Sir, yes, I got it. Average of the two, H1 is given as it is a quality is the wet stream at a 1 as well as at a 2 at a 250 degrees centigrade. So it should be the H1 equal to the HF1 plus X1 into the HFG1. Then H2 can calculate in the same way HF2 plus X2 into the HFG2. At a both
Narendra,
temperature.
Narendra, hold on.
Yeah.
Why do you need H1 and H2?
If you want to take average.
Why do you need average? See, in your system, this liquid is coming out, right, from the bottom.
Yeah.
So,
Yeah.
assume,
Only
let's say at state 1, initially when you just open the wall, what will be the enthalpy of liquid exiting the system or the control volume? See, you know the temperature, right? It is 250
yes.
degrees Celsius. You go to the steam table and you take HF at 250 degrees Celsius.
Yeah.
That will be your enthalpy exiting the system, right?
Yeah.
Exiting the
I have
control
done
volume.
the same thing, sir. I have
Uh,
taken the HF value and
uh,
that 108534, but my answer is coming 7195.39. But that option is not given. Nearer option is 6312 kilojoule positive. I think it should be the positive.
Acha. Have you checked your calculation?
Yes, sir.
Tell me one thing. Uh, like, what is HE1? I mean, like, it should not be written in this way, but anyway, I'll make it correct. Uh, hmm. Hmm. What I'll do, Narendra, I think the time is
Okay,
7:20.
okay, sir. Now
I
even
had,
I will check my any calculation. I am
uh,
getting nearer to that any option. Just
hmm.
there is a difference of something because I know that in this any assignment of NPTL, whatever the questions given, that answers are coming matching exactly to the decimal. I know this.
Hmm.
There is a just difference. That's why I put up that. I am doubting on the HE.
I'll do one thing. I'll solve this on my own, and I'll let you know in the next class. Would that be okay?
Okay, okay.
Because now
Sir,
the class is over. Otherwise, we would have done it.
sir, again, one I want to ask.
Uh,
In the, if you suppose a permit, may I ask, sir, in a assignment and 5, in a correction, even answers are provided, but in the valuation, that correct options are not any chosen.
oh, actually, last time when you told me, something
Yeah,
like last time you told me, I think assignment number 2 it was.
yeah,
So I have informed the person who I know in the NPTL team, and I can do the same, but if you know the correct answer is not that, uh, I mean, I don't know how easy it is to change things here.
in this assignment, there are the three questions.
Which
Therefore, I
question?
lost three questions. So I lost 70 marks, 30 marks. I got only 70.
Uh,
And the number of candidates are put up this one in the question forum, but in the question forum, nobody is any responding. I'm not
uh,
making a complaint that this,
no,
I'm
no.
really any.
Tell me the question number.
No, sir, it is a very correctly, sir. Even answers are an answer sheet, answer key is any given, and in the answer key that given the correct answer. But while
Uh,
selecting the answer, they have selected different answer. For
yeah,
example,
understood. Understood. Tell me which questions you said. Na
okay,
three questions are like this.
okay. Yes,
Uh,
sir. Question number 6.
okay.
Mass of flow rate of the air through the nozzle in a kg. The answer is correct answer is 2.06. I
Okay.
calculated the same, and even in the answer key, same answer is any given there.
Okay.
But while evaluating, they chooses the third option, C option 1.90,
Okay. Okay. So correct option should be
2.06.
which is ABCD. Which one?
A,
And they are taking.
C option
Tell me.
1.90.
Tell me next question.
Then I think last question. There is a 127 and 117.
Question number 10.
Okay. Question number 10. The
Uh,
correct answer is 127,
okay.
and they selected 117 option A.
Okay. Okay. Anything else?
And again, in the problem, question number 8,
Okay.
in the, I think it is a pump
Uh-huh.
in the ranking cycle. The
Mm-hmm.
formula is the W equal to the minus integration of the VDP, V up into P1 minus P2. Here that Vf is at a pressure of that is a 70 condenser pressure, but that
Okay.
they have taken not exact values, they have taken exactly an 1 upon 1000, but exact value is at a 70 kilopascal 0.011036. So for the exact value answer is coming 3.05 C, and for this taking 1 upon 1000 0.001 only, answer is coming 2.93.
Uh, can you repeat the question? It
Question,
is P1 minus P2 by rho, na?
नहीं V up specific volume V up
Uh,
into P1 minus P1 is the boiler pressure, P2 is the condenser pressure. That VF is then calculated at a condenser pressure, lower pressure P2.
Okay.
At a pressure of 70 kilopascal, the value of the VF from the steam table is 0.001036.
Okay.
Exact value. But in the solution, they have taken the value 0.001 only.
Oh,
They have not
because
taken the exact value. That's why there is coming the difference. So with a 0.01001 answer is coming to 93, and with the exact value it is coming the 3.05.
1 second. Tell me the VF at 70 kilopascal.
0.001036.
1 second. 2930 divided by 0.0016.
0.001036.
36. Oh, I should have multiplied. Sorry. 2930 into
Yeah.
0.001036.
36.
Then the answer is 3.3.
0.35448. 8.
No, it is 3.04.
3.04.
So it is C.
Yeah, yes.
Okay. I'll inform the people that I know. Let's hope they'll change it. Okay.
Yes. No, sir, any mass name really that is not or any issue, but at least some explanation we expect.
No. I think the first two, like out of three, the first two are, I think, some mismatch between the
Yeah.
correct options. That is not your fault. That is
Yes, sir.
that is understood. That can be changed. But this question number 8, this begs into the the options should not be this close if the
Yeah.
these things are there.
Okay.
Anyway, I'll forward this doubts or this these questions to the people that I know.
Yeah.
Let's hope they'll change and you'll get your number back.
Okay.
Okay.
Thank you, sir. I have taken more time today.
Hey, no, it is fine. This is the whole point of talking for 1 hour. If you are not there, then anyway. So yeah,
Okay.
this last question that you asked, I'll answer you next class.
Okay, sir.
We'll see. Okay.
Okay. Thank you. Thank you very much, sir.
Okay, sir. Narendra, then shall we stop today for today?
Okay, sir.
Okay.
Okay. Good night, sir.
Good night, Narendra. Have a good night. Bye.
Okay. Bye, sir.